everyone. Cynthia and I are going to be presenting our work on collaborative welding and joint sealing robots with haptic feedback. Cynthia is in the Civil and Environmental Engineering department, and I'm a PhD student at the Stanford Robotics Lab. This work was possible thanks to the collaboration between our two research groups and our industry partners. Let's start by looking at this image. This is the kind of environment where we may find robots nowadays. Assembly lines are highly structured environments, which means that pre-programmed robot motions will actually lead to task success because we know where all the objects are in the scene. The robot performs the same exact task over and over again. And additionally, there are no humans. So as we can see here, the robots are sort of caged in. We don't have to worry about human safety, but it also means we're missing out on the opportunity to collaborate with expert operators. Now let's move on to the kind of environment where we would like to automate tasks. This is a construction site, and it does not have a lot in common with the assembly line from earlier. This is a highly unstructured environment, and therefore pre-programmed motions will not work. If we try to use the same approach as before in an environment that is as dynamic as this one, it is bound to fail. These environments are constantly evolving, there are workers and endless possibilities for automating tasks. So it's pretty exciting, but at the same time, extremely challenging. An option to try and overcome the complexity of this environment is to use teleoperation. This type of approach can work, but it is not very scalable because it requires one robot per operator. And at that point, the robot is not much more than a fancy tool, but it doesn't really have much autonomy. So what we're proposing is to have use a methodology that allows us to combine skilled robots that have autonomous capabilities with human expertise. In order for humans and robots to collaborate, we need some kind of interface. And we chose to use a haptic interface. The haptic interface allows us to feel the contact. So in the same way that your phone may vibrate when you press certain keys, this type of interface applies forces on the human operator, allowing them to feel what the tool that the robot is holding is feeling when it touches the environment. This makes failure from recovery much easier and more effective. You can think of even something simple like inserting the tool into a hole. If you only have vision and see it from an angle close to the hole, it's going to be really tricky to place to insert the tool. Whereas if you can feel it and slide on the surface, it will make it a lot easier. Additionally, we can learn and improve upon the autonomous skills of the robot by recording not only data from the vision, but also from the contact interaction. Next, I'm going to show a video to illustrate how haptics work. So on the top, we see the full scene where an operator, we place this sort of screen in order to demonstrate that it could be done from a faraway location. So the operator you can see on the left has access to vision coming from a camera and also contact. On his screen, we're plotting so that you all can see that we're plotting the forces, the contact forces that are rendered to the operator when the screw touches the surface. And there on the right, you can see the robot operation. So Cynthia's going to explain a little bit more about these haptic controlled robots.
So obviously coming from the construction perspective, these sort of applications with haptics have enormous potential. Think of these painting tasks. If we didn't have the tactile feedback, it would actually be really difficult for the user to complete it. And here we can see that we're leveraging the user expertise and intuition to complete this task. And this is another example from the Stanford Robotics Lab that has also previously worked on a solution for remote high tension cable manipulation. This is, of course, a very hazardous and strenuous task. And here we see the operator can successfully achieve his goals by providing all the input of this complex task haptically. But in this paper, our goal is not only to rely on the human operator with the haptic devices, the vision, and the contact feedback, but it was also important to implement a robot that has some autonomous skills that can be learned and improved with time. So skills like inserting, screwing, tracking an edge, aligning surfaces, and tightening threads, for example. And this obviously can be mixed and matched for different tasks and building elements. And you can see in construction how having this combination can be extremely powerful. And so this possibility to combine both the human expertise through haptic devices, but with some robot autonomous, actually led us to this work and motivated a research project with industry partner Goldbeck. We studied, and as we can see in this video, a 6-level parking structure that has a high level of prefabrication, but still, once we get to the assembly on the field, there are many tasks that need to happen and that are highly repetitive and manual and require a lot of effort from the workers. And these are still pretty difficult to automate today with fully autonomous robots. Most of the current approaches that we're seeing today for construction robots rely on a human operator overseeing a single task semi-autonomous robot, and the operator is in very close proximity to the robot and has the visual feedback. However, if there's an obstacle or an error, the operator input is actually very limited to recover the task, and usually the task has to be completed by manually by a worker. Our human-robot collaboration method explored the combination of the human expertise plus the intuition with the robot skills, because as Elena mentioned, we don't want to completely teleoperate the robot at all times. So if the operator has contact feedback with haptics, as in the examples that we showed previously, then they could control the robot remotely if needed to recover from a failure or if there's an obstacle. So our first step in this research focused on selecting 5 repetitive, strenuous, and high dexterity tasks. So drywalling, bolting, painting, bolting, welding, and joint sealing. The first 2 examples only focus on using this haptic exploration, but without any autonomy. And here, of course, as we mentioned, there are some limitations because we want to be able to still leverage some autonomy. In the third example, we only focus on an autonomous solution, but this approach is likely to fail, especially when we're working in such an unstructured environment as construction. And so here in this research, we focus on the last 2 tasks by going one step further. So we wanted to be able to really combine the haptics and the robot autonomy. So why these 2 tasks? Welding was actually really crucial for the prefabricated parking structure because accuracy issues at this level in the foundation will cause misalignments in the structure of the following levels. So that's why today a really expert worker is the one tasked with placing, fixing, and welding 144 anchor plates to the foundations. And today the process consists of welding the perimeter of these anchors, which takes around 45 minutes per anchor, so around 108 hours in total, just in one parking structure, of which the company obviously repeats all across Germany. The task was interesting to automate for our industry partner because the parking structure also requires 6 kilometers of concrete joints between the prefabricated slabs. And this task involved 3 different crews for pouring concrete, shot blasting, and then finally 3 layers of coating using traditional methods, such as connect module machine that is worked by one operator. The sequence was also quite important for the structural integrity and had to be repeated for each layer, making sure the joint is completely filled. So as we can see, this would be something that is still difficult for a human to remember and has to keep track of this specific order, but would be actually easier for a robot to complete. And here we could see opportunities to navigate using a mix of vision and pressure sensor from the robot perspective. The method that we used to develop these human-robot collaboration approaches for the task consisted of 4 steps. First, as you saw, we collected the production data of the manual approach on the field. Second, we generated a realistic simulation world based on the building information model provided by the industry partner at level of development 300. And third, we iterated on autonomous behaviors that allow the robot to interact with the environment. And here, because we were working in simulation, it was easy to get quick feedback from the industry partner. And then finally, we established the flexible control framework that allows for seamless haptic intervention when needed. And now Elena will walk us through the solution in more detail.
Cool, thanks Cynthia for that intro. So we're gonna go into a video with some of the experimental results for the welding task. And here's a still of what you're gonna see in that video. On the left, you see the simulation world and what the robot is doing in that realistic environment. In the center, we have both the sensed forces by the robot and the perceived forces by the operator. We can see that in that bottom plot, the perceived forces do not exactly match the sensed forces. And I will go into more detail about how that works after the video. On the right, we have the operator intervention. So what the operator is doing whenever the robot requires some help. So we can see that it starts off in autonomous mode, it gets close to the plate, and then we can switch to this haptic collaboration mode where the operator is exploring the plate and tracking the edge. Now, once it's done, we can see that while it's performing the haptic task, it's sensing those forces, and the forces are being rendered to the operator. Now it's back in autonomous mode, it can go to the next plate, and again, we can switch back and forth. So the operator, if he sees that the robot needs help or simply wants to explore the environment further, can take over the task. So let's move now to how this collaborative control really works. We can see in the plot that the simplest cases in which the perceived forces and the sensed forces are the same. A slight upgrade from that would be if we apply a scaling factor to the sensed forces so that the human, an example where that might be helpful is, let's say you're trying to align a beam, one of those heavy beams that we saw in the video that Cynthia showed earlier from the parking structure. And we want some feedback to know if we're aligned or not. We want to feel that, but we don't want to feel all 200 pounds of the beam. So that's where a scaling would be pretty helpful. And if we take it one step further, we can have that the perceived force is the sense force plus what we call an egg force. In the case of the video we saw earlier, the force in the negative z direction, so pulling us down towards the ground plane, is larger than the actual sensed force by the robot. And this is in order to make the task a little easier for the operator. So if he's trying to track the edge along the ground, then the operator now doesn't need to worry about all 3 degrees of freedom of the task. It just needs to worry about the X and Y, what area it wants to explore, and this additional force in the Z will kind of, like a magnet, attract it down towards the ground. During this task, we explored some other areas that can be a little tricky if you're using pretty, cheap makes it sound bad, affordable haptic interface. So the really good news is that these algorithms can work on this affordable device, but then it's got some limitations because the workspace of a device like this one is pretty limited, whereas we're trying to control this mobile robot that can explore a big workspace. So you can think about it a little bit like a mouse and a mouse pad. So if this was the haptic device, then once you reach the limit of the pad, you can lift it And now the cursor won't be moving. You're moving the haptic device, but the cursor is still. The cursor would be the tool on the robot. And then you center it again, and then you start controlling again. That's the idea behind this workspace extension that we implemented, and that allows us to explore a large workspace with a very small, affordable device. Finally, let's move on to the second task. I'm going to go quickly over the steps that we use, which is the same methodology that Cynthia introduced earlier, where we first collected on-site manual data of the task, generated a realistic simulation world using the BIM files, developed autonomous skills in order for the robot to fully autonomously attempt to perform the task. But because we're in a very dynamic, unstructured environment, we want to at least have the option to intervene effectively and be able to feel the environment. And that's where we incorporate the haptic collaboration framework. So we bring in the autonomous capabilities of the robot and allow for haptic control when needed. Here is a quick video of the results for the joint sealing task, where again, it starts in autonomous mode, and then the operator can switch to a haptic collaboration mode whenever, for example, if it gets stuck on one of the joint at the intersection. Thanks to a little pressure sensor at the tip, these forces are rendered back to the operator that can get it unstuck and have it continue the task autonomously. For the joint sealing task, we explored further what the framework for improving the autonomous skills of the robot could look like. We start off with human demonstrations of the complete task. By analyzing this data, we can learn some skills and code an autonomous controller for the robot to perform the task. Now, there might not be failures, in which case the task will be completed, and that's great. But in a very dynamic environment like a construction site, there could also quite likely be some failures or new scenarios that the robot doesn't know how to handle yet at some point. And that's where the haptic control comes into play. We can then collect data, both visual and contact data, from this failure recovery strategy used by the human, which we can then combine with the original task demonstrations in order to better understand the task, further develop our skills, and improve the autonomous controller, which will, in the end, lead to a higher success rate for the task. Having gone over these two tasks, I want to go back to this diagram that Cynthia introduced at the beginning that summarizes well the framework developed and tested in the two tasks presented in the paper. So we have a human operator and a robot with a set of autonomous skills that can be recombined to perform different tasks. They're both getting feedback from vision and contact in order to, in the case of the robot, perform the task autonomously, request help when it senses that it's in a state it hasn't seen or it doesn't know how to handle, and on the human operator side, to more intuitively intervene. We made all of our code open source, and it's on GitHub, and we've also made our data set public and are slowly building and enlarging this data set. Big thank you to all of our collaborators, especially Tracy, who made huge contributions on the welding task. And thank you also to our lab mate, Adrian Piedra, who is a great haptic operator, much better than me, and helped us a lot with the videos. Thank you also all for listening, and we look forward to your questions.